In the last tutorial, we started up DSP Explorer for the first time and wrote our first DSP program, which was a simple signal generator. We then ran the signal generator and examined the generated signals using the oscilloscope and spectrum analyzer features of DSP Explorer. In this tutorial, we will expand the capabilities of the signal generator to make it more useful. We will then use the signal generator to explore the two principal types of DSP signals. These two types are referred to as real and analytic. Before delving too deeply into the differences, let's write some more code by expanding our signal generator. I would like to add the following features to our signal generator. First, the ability to sweep frequencies. Second, the ability to adjust the sweep rate. Third, to be more precise about the signal frequency being generated. And fourth, to shape the waveform so that it can be recognized on the scope. You are probably tired of watching me type programs, so I'm going to load my updated version. A few aspects of this new module should be pointed out. First, my modules always start with the parameters at the top of the program. You can see my parameters up here. A lower frequency, an upper frequency, a period over which I want the signal to be precise, the increment, which is essentially the scan rate, and a signal I'll call ramp and explain in a moment. The next thing I do is list my inputs and my outputs. Of course, there are no inputs to the Siggen model. You can actually put the output declarations anywhere, but I put them at the top. After the inputs and outputs, I declare the variables I'm going to use. Our frequency, the direction that we're sweeping, the amplitude of the signal, and the phase of the signal. DSP Explorer allows you to declare the variables any time before you use them. Some programmers declare variables immediately before their use. Others declare variables at the top. I mix and match the styles, which is probably bad, but there it is. As we saw in the first tutorial, variables are initialized to 0 at compile time. However, there are times when we would like to initialize a variable to something other than 0. This can be done using a construct called once. The statement immediately following the once keyword is executed the first time the module is called, but is skipped over all other times. Here is an example of once. In essence, I'm saying if the lower and the upper frequency are different, then the direction is the increment. Otherwise, the direction will remain 0. Now comes the real code. It is very straightforward. First, we update our frequency, and then we check to see if the frequency is too low. We reset it to the lower bound and change our direction. If the frequency is too high, we set it to the high limit and change our direction again. Given this new frequency, we advance the phase. Notice here that we will advance the phase a complete cycle, a value of 1, once every period. As I said at the beginning, I wanted to be able to shape the waveform so that it could be easily recognized. I do this here by adjusting the amplitude of the signal as a function of the frequency. As the frequency goes up, the amplitude will also increase. We'll see this in a moment. Having computed the amplitude and the phase, we can now produce the I and Q signals. I would like the I and Q signals to advance one full cycle each time the phase advances by 1. This would mean that I would have to multiply the phase by 2 pi. Honestly, I got tired of doing this, so I provided cosine 2p and sine 2p, which essentially is cosine times this value, phase, times 2 pi. This is one of the advantages of writing one's own tools. Let's see some signals. Let's set the lower bound to 1, the upper bound to 5, set the ramp to 1, and run it. Well, let's set a trigger first. Trigger, Siggen, the I signal, and we'll set the scale down, and let's change the sweep frequency. There we go. I is what is called a real signal. It is real because it can be expressed using a single variable. For our purposes, it is like any signal we might have in an electronic circuit. Note that if we look at the spectrum of I, there will be two peaks. Here and here. Let's change the scale. In DSP parlance, the right-hand peak is called the positive frequency, and the left-hand peak is called the negative frequency. There are many folks who don't believe there can be a negative frequency, and if you are one of them, just make believe that the concept of negative frequency is a mathematical convenience. Now let's look at the S signal. Again, the S signal is just the combination of the I and Q. If we look at the spectrum of this signal, we'll see a single peak. For those of us who think of electronic circuits, the S signal requires two signals we usually call, no surprise, the I and Q channels. Notice that when we look at the magnitude of the S signal, it is twice the magnitude of I or Q. Set these scales to be the same, and you can see that it's basically twice the magnitude. Let's look at what happens when we mix the various forms of signals. Remember that mixing is simply multiplication. Let's add a mixed signal generator and set it to 10. Now we'll add a math module so that we can do some multiplication. And we want to look at the signals inside the math model. So we'll add A, and we'll add B.